So first of all, I have a question for the audience, and this is specifically students and even faculty. In the civil engineering curriculum, at least to my mind, I don't think there's a whole lot at the undergraduate level, even at the graduate level, a whole lot of hands-on instrumentation courses. And I'd just like to see how many people have taken those, or how many universities have hands-on instrumentation. It looks like one over there. Any? So just a few. That's the general thing. Mechanical engineering, it's part of the curriculum. Aerospace, it's part of the curriculum, but it's not in civil engineering, and that's a weakness that I think NEES needs to help fill. And I've talked to several of my colleagues about having events like this, instrumentation symposiums, and we may even talk about having some sort of instrumentation course for grad students and young faculty to get them over that hurdle, because it's really easy now to go to a catalog and to take measurements. It's really hard to do it right, and it's easy to make mistakes because you can just buy stuff. You can go to National Instruments and buy data acquisition and hook up an accelerometer, a MEMS accelerometer, but it may be the wrong thing. So that kind of information is available, professional organizations and vendors, and I'll give a couple examples of things that I have used in my teaching and that I've used for myself, for educating myself on some of these issues, because it's a continuing learning for all of us, even us instrumentation experts. It's a continuing process of making mistakes and improving. So this is one, ASCE. IEEE does a lot more of this, but this is the first I've seen in ASCE. They actually have instrumentation monitoring boot camp that they're advertising in December and then in February. And it's a really good curriculum. The only problem with ASCE courses is it costs $1,500 or something like that, which is sometimes tough for students and young faculty to afford. But these are the kind of topics that need to be understood by people who are trying to use NEES and trying to interpret NEES data. So it's sensors, strain, load, pressure, deformation, tilts, motions. Data acquisition is important. You really cannot just start buying a National Instruments system and hope to get good data right away. I mean, just as an example, a lot of the National Instruments cards don't have anti-aliasing filters on them. Problem right away. There's a lot of stuff out there. A lot of the vendors have sort of hidden in their materials some good freebies. This is a really good guide. If I were teaching a course in measurements, I would probably use this as a textbook. It's 100 pages. It really does thoroughly go through most of the issues that one would need to know at a basic level. And I think the websites. This is something that was written by IO Tech, and IO Tech is now part of measurement computing, so it's the usual corporate thing, big fish swallowing a small fish, but this is basically an IO Tech product. They've also got on-demand tutorials, videos, slide sets, which are really good, really quite good, and they're free. And again, the same thing, MCDAC, MCCDAC, if you go there, you get a lot at their resource center. It's a lot of good stuff. This is one of the most proactive companies that I've found. National Instruments has a bunch of stuff. Some of it you have to pay for. Actually, a lot of it you have to pay for. But there is some good stuff. And they have this down here, NI Elvis, which is a curriculum for instrumentation that looks pretty good. But again, that part's not free. This is really good. This is Professor, let me get his name right, Muratore, a mechanical engineering instructor at Rice. just put all his slides for free on National Instruments. It's a whole quarter course in instrumentation. He's got all his PowerPoints there, and I borrowed a few of them for my presentation. So, but it's really it's pretty well done, coming at it from an aerospace point of view. So there's lots of stuff out there, but and I do recommend that that grad students and young faculty, and even older faculty, and even us guys who think we're experts, take advantage of these because it's just not done enough in civil engineering. And I know all of the site managers and the NEES site people encounter problems because of that. So a quick review of basic instrumentation issues. And some of the other talks in here will go into this in detail, but the basic purpose of instrumentation that we use in NEES and elsewhere is to translate a physical phenomenon into numbers in an accurate way. So you've got some sort of physical phenomena. You've got transducers or sensors. Those are somewhat synonymous, not quite. You've got some sort of signal conditioning, because transducers produce either an analog or a digital signal that needs to be converted into computer language. You've got data acquisition and then a computer of some sort. There's analog and digital signals, counters and timers and different types of sensors. All that's way beyond what I can do in a brief talk here, but those are the basic blocks. And a typical system, and I said now it's easy. Now you just buy stuff off the shelf. And for the most part, it works reasonably well. In typical instrumentation now, you buy a sensor of acceleration, displacement, force, whatever. You put it into a signal conditioner, and if National Instruments, that's probably on the same board. But that contains power, bridge completion if you need it, amplification, filtering, etc. And then you run it into a data acquisition unit. And again, this 10 years ago, 20 years ago, this was not invisible. Now it's invisible. It's generally done well enough that you don't have to worry about it too much. You still have to worry about resolution and sample rates and those basic issues, but you don't have to really know what's happening inside, that there's a sample and hold that has weird skews or anything like that. It's generally handled pretty well. Analog to digital converters have converged. They're now kind of errors that we had 20, 30 years ago are just not there. So this is a pretty mature field. Recording, storage, and display is easy now. It's easy to take measurements. But this is what it looks like when we get in the field. And this is where you really need to know what you're doing. When you come out in the field or in the lab and start hooking up more than just a few sensors. This is a wind turbine monitoring experiment. I think many will recognize this is acceleration, so those are kinemetrics, orange boxes, and I don't think there's any accelerometers in the field of view here, but this was all accelerometers. There's one of our field projects with our one of the UCLA shakers, our big shaker. We call this Popeye. It's a 100,000-pound shaker. And there's a few sensors out here. You see a fairly small bundle of cables. Most of what we do in civil engineering is modest in terms of size. This is a fairly dense bundle. This is an instrumented pile that we did at UCLA. This has displacement sensors, regular resistance strain gauges, and fiber optic strain gauges. You see some fiber optic cables in there. A fairly dense bundle that I'm sure many NEES site managers and many people who do large-scale experiments have seen instrumentation this dense before. So this is nothing new, but as I said, this is still modest. This pile had 100 channels of strain gauges or something, and actually it's about 50. In other fields, we talk about tens or hundreds of channels. In other fields, aerospace, mechanical, physics, geophysics, they talk about thousands of channels. This is just a picture I dragged up of some sort of aerospace dynamic testing. And you can see these huge bundles of cables. There's probably 10,000 channels in this whole array. The caption that under this picture said that this was one module, and they had 10 of those modules stacked up down there. So what we do is, in the global scheme of things, pretty simple in terms of number of channels. But what that means is that we really don't get that good at it. I mean, very few of us use things like TEDS, Transducer Electronic Data Sheet, which automatically identifies sensors. You don't have to go out and physically touch a sensor and write down a serial number. It's done electronically. A few of the NEES labs do that, but for tens of sensors it doesn't make sense. For thousands it makes a whole lot of sense. Things like that we just don't touch on. Mung goes out and does vibration tests to the ground where you have dozens of sensors. When the oil companies do geophysical exploration, they have thousands of sensors in sensor lines that are miles long. So the stuff we do is fairly modest. And the stuff that we measure is pretty straightforward. We're measuring steel and concrete. We're pushing and breaking things, so we're measuring linear position, very rarely angular position or velocity, but linear position, linear velocity, acceleration, strains, and forces and pressures we usually measure via strain. It all comes down to a strain gauge somewhere. So those are the most common things that we encounter. This table I grabbed from Muratori's course. And it just basically says the same thing I did, that linear position, there's some direct measurements, potentiometers, LVDTs, time of flight measurements, lasers, sonar, velocities, direct measurement, or integrated acceleration, or differentiate position. And then acceleration is essentially force divided by mass in most cases. And pressure is force per unit area, so it's, again, getting back to force. Angular, I don't know, do any of the NEES sites actually take angular measurements? Anyone?
Yes.
You do?
In underground pipelines.
Okay.
We use LVDTs in joints.
Okay.
To find out what's the relative.
But those are those angular LVDTs or just linear combination? Okay.
You need minimum 3.
Yeah.
To get the rotation.
Yeah, because there are in aerospace in many areas you're using direct angular sensors. There are angular LVDTs, rotary variable differential transformers, angular accelerations. As a matter of fact, I was supposed to be taking off tomorrow to the second international workshop on rotational seismology that is worried about direct measurement of ground motion, rotational ground motion during earthquakes. But we don't do a whole lot of that in civil engineering. I think we should. There was a lot of discussion about in the blind prediction today about problems with rotations, with moments and rotations, predicting those, and part of that's because we don't measure them directly.